Welcome back. So now we are going to focus on the language models. I did not call it large language models, even though that's the direction that it goes to. Even though ChatGPT and LLMs are kind of new, the idea of language models is not new at all. In fact, it's been decades since we've been doing this. They didn't have, of course, the power, the expressive power of a chatbots like they have today. But somehow they are very interesting to look into, and especially because it's very easy to implement. So in fact, you can take what I will show you today, and you can implement something like that in Python, and actually implement a mini ChatGPT. Of course, that wouldn't be as elaborate, but in a quite simple way. So here's how it's going to work. Does anybody remember these things? Finite state automaton. Has anybody ever seen that? Who never saw something like this? Okay. So I'm going to guide you through it. So even if you haven't seen that before, to make sure that you understand what's going on. It's an automaton, it's a machine. It's like playing a game. So the idea is that you have here this graph of nodes. The nodes are called states. And then you have edges that connect the states, and then you have labels on the edges, right? A and B. I just use A and B. These are the letters, right? A and B. You could have more. You can have the whole alphabet or anything. What is also important is that you have a start and an end. The start is labeled like this. It's like how you enter the maze. So you enter here, start. That's the node. And the idea is that you win the game if you end here, right? You just need to traverse the maze according to some way that I will tell you about. And then if you end up here, then ding, 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 you won, okay? That's how it works. You have an equivalent representation of what I've shown you if you actually give numbers to the nodes. So you just call them 1, 2, 3, 4, 5. I even threw in some colors. The idea of that is that the edges that you have on the graph, this is called a transition table. This table here is equivalent to the graph. It's not something new, but let me explain how it corresponds to the graph for those who don't know. Imagine that you are at node number 2 right here. So this is where you are. Basically, A brings you to 3, and B brings you to 5. Who agrees with that? Well, you just write it down here, right? A brings you to 4, and B brings you to 5. This is a transition table, but again, displaying it as a graph might be easier to play the game. The table here might be more of a Python representation in memory when you implement it. Okay, so let's play the game then. The way you play the game is that there is some input that is a word that is made of the letters that appear in the graph. So in that case, I just have A and B, but of course it could be more, but let's just put A and B. And my word is ba, right? I take that word, B-A-A-A-A. So the way it works is like this. I start here, right? And I put my little cursor to say exactly where I am. And then I just eat. It's like Pac-Man, right? So you eat the letters one by one, and every time you eat a letter, you just move in the graph. For example, if I eat B, then I'm going to end up here, right? And I just move by one position, okay? Then if I eat A, I'm going one more to the right. If I again eat A, one more to the right. And now A, I'm staying where I am. That's a loop, right? Just loops back on the same node. Then A. And now you see I'm done consuming the word, and I'm in the winning zone. So in that case, what I say is that I accept the word. Ba-a-a-a-a is accepted. No, ba-a-a-a is accepted. Ba-a-a-a would be accepted too, but this one is accepted. Now, can anybody give me an example of word that would not be accepted? Anybody has an example? Anybody? Yes? 3 B's and away. Yes, absolutely. You see, if you play with this, starting here, 3 B's, so B, 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 and then you're here, and actually then it's an infinite loop, right? Once you're here, you're stuck. That's basically a thing. Somebody else on Zoom says A, and yes, absolutely. If you follow A, then you're here. In fact, it's a trap. As soon as you're here, it's done, right, by the construction of the game. So what is this machine? Well, you can see it as a game, but in fact, it's a machine that says yes or no. It's a machine that, if you feed it with a word, says, yes, I accept that word, or no, I do not accept that word. Is everything clear? So basically, what that gives me, here's another one. B, A, B, A, you don't accept it. So what it does is that it splits the set of words into those I accept and those I don't accept, right? By the way, if you want to go formal, but I'm not doing it today, you can actually use delta, sigma, like this is the typical notation when it's taught in the classes. So basically, if you consider the set that contains all of the words that you accept with that machine, you call it D. It's a set of documents. And that's called my language space, right? In fact, it's called a language. A language is a set of strings. And it turns out that there are some properties of some of these sets of strings that are called, for example, regular. It's also, you can express it with a regular expression. And it turns out that you can also express it with a machine like that. There's all these equivalent representations. Who heard of regular expressions? I assume anybody who heard of this also heard of regular expressions, right? Okay, so the idea is that I have this set that my machine accepts. And if I modify the machine, then it's going to accept a different set of strings. Now, what I'm going to do that you might not have done before is that I'm going to equip this set with a probability distribution. In fact, I'm going to use that as a random variable over the documents. So remember my document D, that's a random variable. We've seen that before, right? So imagine I have a random variable uppercase D. We have an omega space that I'm not showing, but basically it's my little elves that each have a document. And then E subscript D is the probability that I get over the documents. And the probability for every document, if I sum them over the document, gives me 1. Who is with me? Okay, so big D is a random variable. And again, you can also write it down this way if you prefer. Some people prefer to write probability that big D, the random variables, equals small d, which is the document that you're currently considering. Okay, now let's get to the elves. Can we use the elves in a different way? This is so cool to have everybody should have a facility in Antarctica because you can do really a lot of things with that. So let's continue to ask the elves to contribute. So these little elves now are going to be used to generate documents. So it means that I'm giving the elves a machine like this automaton, but instead of consuming documents and spitting yes or no, they are going to create documents with this machine. So the question is, how do we turn this into a generator? And the way you turn this into a generator is to just walk through it randomly, right? You start on the left and then you pick at random, so we can add some probabilities in there. I just need to make sure that the probability distribution at every node sums up to 1 for the outgoing edges, right? For example, at the start node, I have 1/2 B, 1/2 A. I put 1/2 everywhere here, technically, okay? So these are my probabilities. And I put a stop also over there because otherwise it's forever, right? So I need to make sure that it stops at some point. So now I'm basically asking my little elves to, this is one elf on the top right, that's going to take the start and, just like this, tack, 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 and they are contributing the documents. The probability for that one is 1 in 64. So every elf in 64 is going to give me ba as an output document, right? Who is with me? Yeah. All right, so now let's look at it a little bit formally. So I have a random document. It's a random variable that's a document, that's big D. And remember, a random variable is a function from omega to some set. What is that set of documents, in fact? Well, in that case, do you agree that the order is important? Now, if you consider that B and A, these are terms, and the thing that I get in the end is a list of terms, then we basically get the list of word semantics, right? Because the order is important. It's B, then A, then A, then A. The order is important. when the order is important, the notation that is used in theoretical computer science is the clean star like this. That basically means that you're looking at all the sequences of terms where the order matters. It has a monoid structure. Who remembers what a monoid is? You never saw monoids? Who saw a monoid already? Okay. It doesn't matter really if you know. It's just basically, it's a mathematical structure where you have a set and you have an operation over that set that is concatenation. It means that if you have the set of strings, you take one string, you can concatenate them in another string, and that is the concatenation operator. You can check that it's associative, but it's not commutative. That's what makes it interesting. What is the neutral element for concatenation? What string? Yes? The empty string, exactly. So it has a neutral element, and it has an operator that is associative. And it's not invertible, right? You don't have an inverse, or don't necessarily have an inverse. So basically, when you have that structure that uses concatenation, and in fact, we use concatenation here because we keep concatenating terms, we just write it T star, where T is a set of terms, right? So I have my million terms in T, and then T star is basically the set of all the documents that are lists of terms, right? Okay, so now I have my random documents, and that's the list of words model. I could also derive another random variable from that is the length of the document. It's a function of D, so by transitivity, it's a function of omega as well, right? So in here, I just forget about the content of the document. All I look at is the length of the document. So in that case, that would be 4, right? It has 4 terms in there. Okay. So far, so good? Everybody with me? Okay. So imagine the little elves that generate documents at random by walking through that graph, you know, tossing coins and building documents by concatenating terms randomly, but according to that very specific automata. Okay. Now, how do we get these automata? Because I showed you one example of automaton here, that's just one, but you can build many of them, right? There's many ways to build automata. So what we are going to do now is that we are going to generate plenty of these automata from the actual documents in my collection. So imagine that I have this gigantic library with 1 billion books, right? And for every one of these 1 billion books, I generate, according to some rules, an automaton like that. Every book in the library gives me an automaton. Now remember that I have septillions of elves, right? So that's easy. I can just distribute the book, and every elf is going to get maybe a quintillion, no, sorry, every book will go to a quadrillion elves, right? So a lot of elves will process the same document. And all of the elves with the same document end up with the same machine, right? And all the elves that have a document will produce some other documents, some new documents that are generated according to the initial documents. In fact, if I had told you that 2 years ago, that might have been a bit confusing. But now that there is ChatGPT, it's very easy to explain, right? Because the initial document is basically what you fed ChatGPT with when they downloaded the internet and put all the news articles and so on. And the documents that you generate at random, these are just the answers of ChatGPT, right? So now it's kind of intuitive to understand. For whom is that intuitive? Right? So the idea is that we turn the actual data, the training data, the documents, into generators of new documents that look alike, that look like the original documents. Okay. That was scary, right? Okay, let's go through that one. Okay, what's going on here? Don't be scared. This is a use of the chain rule. You remember the chain rule. It's basically the idea that when you have a probability of many events, the intersection of many events, you can turn that into a chain. The idea is that the probability that is both raining and I have my umbrella, that's the probability that it's raining, times the probability that I have my umbrella, given that it's raining. It's the chain rule. So an example is probability of A, B, and C is the probability of A, times the probability of B knowing A, times the probability of C knowing A and B. Who agrees? It's just the chain rule. I'm using the chain rule right here. Let me show you how. I'm basically computing the probability that my document is exactly D1, D2, D3. These are just the terms at position 1, position 2, position 3. This is not a vector. This is not the same as previously with a vector. This is really the first term, the second term, and the third term of my documents here. So what's the probability that a little elf, to whom I gave the latest Dan Brown novel, spit D1, D2, D3? What's the probability? Well, let's start as a conjunction of several events. First, you would have the length. You need the length to be at least 1, right? So let's take the probability that the length is at least 1. What else do we need? We need, given that the length is at least 1, that the first term is D1, right? Now what I get here is the probability that the length is at least 1 and the first term is D1. So now that we have these two, so I know that the first term is D1 and the length is at least 1, the third thing that comes in is the probability that the length is at least 2, knowing that it's at least 1 and that the first term is D1. Now, I know at that point that the length is at least 2 and the first term is D1. I dropped the at least 1 because it implies the other, right? If I know it's at least 2, then I also know it's at least 1. So this is why this one now goes away. So, oh, that's an extra character. So condition on the fact that the length is at least 2 and the first term is D1, what is the probability that the second term is D2, right? Now, if I know that the second term is D2, the first one is D1, and the length is at least 2, what's the probability the length is at least 3? And then if I know that the length is at least 3 and my first two terms are D1, D2, what's the probability knowing that the third term is D3? And then once I know that my first three terms are D1, D2, D3, and the length is at least 3, what is the probability? It's exactly 3, meaning we stop. Who agrees with that formula? Right? It's really just a reasoning. If I want my document to be, I don't know, I love information retrieval, then that would be the probability that my document has at least one word times the probability that the first term is I, knowing that it's at least 1, times the probability that the length is at least 2, knowing the first term is I, times the probability that the second term is love, given that the first one is I and the length is at least 2, times the probability the length is at least 3, knowing that it starts with I love and the length is at least 2, times the probability that the third term is information, given that it starts with I love and the length is at least 3, and so on, right? I just build that as a succession of new information that at the end gives me the entire document. Now, we are going to give names to these. For example, the probability that it stops, it's basically the probability that the length is equal to something, given that it's at least that. That's the probability of stopping. And this is 1 minus, right? This is the probability that it does not stop, right? The opposite of that would be the length is at least 4, right? So this is 1 minus. So we make an assumption here. We assume that these are all equal. The probability that it doesn't stop is always the same number, and the probability that it stops is always the same number. I just call it p stop, right? So this is basically 1 minus p stop cube, 3 times p stop. And then we have the probabilities of the terms. And then, so that's the first thing, right? So 1 minus p stop and p stop that I call here. Then there is another simplifying rule that I'm going to use. It's called the Markov rule. Who has ever heard of the Markov rule, Markov chains? Who never heard of Markov chains? Everybody heard of Markov chains? Wow, this is fantastic, makes it easier. So the idea of a Markov chain is that you have a limited memory and you cannot remember what happened more than 5 minutes ago, for example. So it means that you only remember the previous n terms, but you forget about the others. So it means that when you compute the probability that the kth term is going to be decay, given the previous terms and that there is a kth term, you basically remove everything that comes before. You drop D1, you drop D2, you drop everything except the last n, right? So you have k minus 1 all the way to k minus n. Everything that's before you forget, right? That's called the Markov rule. It means that you don't even use the previous terms before the last n in the probability. Who is with me? Okay. So let me use a Markov rule with n equals 2. I only remember the previous two words. So it means that if I write now the probability of D1, D2, D3, D4, it's 1 minus p stop. That was my the first one I had here. So 1 minus p stop, the probability that it doesn't stop, times the probability that my first term is D1. Then again, 1 minus p stop. Then the probability of D2 given D1. Then 1 minus p stop. Then the probability of D3 given the first two. Then 1 minus p stop. Then the probability of D4 given the second and the third. And here we drop the first one. Why? Because we use n equals 2 for the Markov rule. I forgot D1 at that point. I only remember the last two. And then p stop. Who would be able to write that for any length of documents and for any value of n? Kind of, right? Do it as an exercise. Like take a document of length 6, D1, D2, D3, D4, D6, and try to write it for a Markov rule with n equals 3, for example. That's a good exercise. Now, what we say is that we have, in that case, it's n equals 2, we have 3 grams. It means that we have a sliding window with D1, D2, D3, and then D2, D3, D4, and so on. It's a sliding window that has a certain size and that I slide over, right? So this is the idea. And the k grams we've seen before, but we saw the k grams in terms of the letters in a term, right? And now we look at the k grams in terms of terms in a document, right? So it's slightly different. Okay. So we are going to focus on a simpler case because this is kind of complicated where we have to remember a lot of things. So imagine that I'm going to use a Markov rule with n equals 0. It means that I just do not remember anything ever. I always forget the previous term. So if that happens, then basically all my conditional probabilities, so they go away, right? All I know is that there is a kth word, the length is at least k, but that's it. I just forgot about the previous terms. So the way it goes concretely is that when that happens, all you need is one number for every term. It's the probability of that the kth term is dk, given that it's at least that long. All you need is one probability assignment, one number assignment for every term. For example, you could have this contingency table that tells you 2 appears with probability 0.3, B appears with probability 0.2, and so on, right? With that table, you could ask the little elves to generate documents using that formula right here. It's just basically 1 minus p stop times the probability of 2, then 1 minus p stop times the probability of B, then 1 minus p stop times the probability of OR. Then you can compute the probability of 2B or not 2B, for example. Who would be able to compute the probability of 2B or not 2B given that table and some value for p stop? Who wouldn't? Who doesn't know? Okay. Who doesn't know if they know, if they could? Who doesn't know if they know, if they know, if they could? Trying to get raised hands. Okay. Okay. So let's just do it together. The probability of 2B or not 2B, given that table, and let's take a p stop of, I don't know, 0.2, right? P stop is 0.2. So 1 minus p stop is 0.8. Probability it doesn't stop. Then the probability of 2B or not 2B. Does anybody want to give me the product? Otherwise, I'll do it. I'll do it then. Okay. So it always starts with 1 minus p stop, right? So 0.8 times 0.3 times 0.8 times 0.2 times 0.8 times 0.1 times 0.8 times 0.05 times 0.8 times 0.3 times 0.8 times 0.2 times 0.2. It stops. Who understood? Right? It's just a multiplication where it doesn't stop, then it's 2, then it doesn't stop, then it's B, then it doesn't stop, then it's OR, then it doesn't stop, then it's not, then it doesn't stop, then it's 2, then it doesn't stop, then it's B, it stops. Right? And if all of that is independent, and that we assume because of the Markov rule with n equals 0, then we just get the probability that the document is to be or not to be as a simple multiplication of these numbers. Right? This is called a Unigram model. We often have questions like this at the exam. We give you some sentences, we give you the table, and we ask, okay, what's the probability of the sentence? We are trying to arrange a calculator with the exams office. You know that this is something that was requested in the past. Okay, so having done that, who now, if I tell you any other sentence like to not is or be, who would be able to compute the probability? Okay, now I see more raised hands. Very good. Try to do it also offline. This is basically just the Unigram model, right? And it corresponds to this automaton where you every time can stop or not stop. So you have 1 minus p stop times whatever probability depending on your word. And then when you have the p stop, then you basically win. You basically end up in the winning area. Okay, so now I did it with actual numbers. What if we actually write down the formula? Just the formula of what I've just done. It's basically this. It's exactly what I've done with the example of to be and not to be, right? So it's 1 minus p stop, then the probability for the first term, then 1 minus p stop, probability for the second term, 1 minus p stop, probability for the third term, and p stop. It's that simple. It's a simple product of numbers. That's the Unigram model. Okay. I'm just pondering if I should stop here rather than annoy you with the multinomial model. Who is scared of the multinomial model? You're not scared? You're not scared at all? Okay, then a quick preview, but don't worry, I'll come back to this next week. What we'll do next week is that we'll try to drop the order. Because in fact, if you think of it in the Unigram model, you never remember anything. So in fact, in the Unigram model, you could argue that the order shouldn't matter, right? So in that case, you basically go from lists of words to bags of words, and you can basically land in a different area where instead of looking at that monoid that is the list of word model, you end up with a vector of term frequencies. That's familiar, isn't it? The bag of words, the vector of term frequencies, the TFs in the vector. And in order to do this, we'll have to consider all the possible orderings of these documents, and all the documents that are the same up to some order, we group together, right? And if we actually do that, it's a multinomial distribution. Who is scared of that? You're still not scared, because that's very scary. But I'm stopping here, don't worry, I'll come back to that. It's called the multinomial distribution. It's less scary than it actually seems. Okay, that was just a preview for next week. Let's stop here. Let's stop on that way, really offline, try to think about for the Unigram model, n equals 0, how to compute the probability that the little elf is going to generate a specific document. Okay, so thank you very much for attending today's lecture. I hope you enjoy it. I hope you will also enjoy the exercises. I think, is it already the probabilities today? Oh, evaluation. So that's good. You have an offset with the exercises. So you'll do the probabilities next week. And this week, evaluation, precision, recall, and so on. Okay, so have a nice lunch. Enjoy your meal. And I'll see you next week for the end of the language models. Okay, thank you very much. Goodbye.